probably should have been, and I wasn't. Um, thank you, Calvin. Whoops. Anyway, so this semi-truck has no brakes, and it goes down the ramp. At the bottom, it hits a runaway truck ramp with gravel. So there's no friction from A to B. There is friction from B to C. And when we do these types of problems, I'll come back to what all this stuff is, but, or maybe I'll just write them at the top, I don't know. But really what I wanna do is energy at A, where the truck is at the top, and energy at B, where the truck is at the bottom, and then energy at C, where the truck stops due to friction. And we kind of did this problem somewhere, I don't remember. I think we did the sliding block or whatever in a quiz or whatever. But we know at the top of this, all you really have to do, you don't even have to think. You can write EA is mgha plus mva squared over 2 plus, there's no spring in this problem. So, and there's nothing rotating, at least right now, there's nothing rotating. So I'm gonna leave it at that. And I just write that for everything. There's gonna be a trick because of the friction that we have to do, but and then our job is pretty simple. We just need to figure out for A, B, and C what H and what V are, if we know them or if we don't. So H for A, I gave you in this problem as 44 meters right here. So I can write down 44, it's positive 44 meters. V I gave as 33 meters per second. And then at B, when it gets to the bottom here, we know that H is 0 at the bottom, okay? So we can write 0. And then at C, we don't know what H2 will be. So we don't know this, and we don't know this. We do know at C though that V will be 0 because it comes to rest. Are you guys okay with that? That's the first thing you do, is write down just the types of energy and then figure out what your variables are from the situation. Once we do this, we know that there's friction. And when there's friction, friction either needs to be put at energy initial is equal to energy final plus work of friction, where work of friction has no sign. It's mu n times the distance, or the initial energy minus the work of friction is E final, okay? And in this problem, what we either need to do is we can set EA equal to EB, and we can set both of them equal to EC plus work of friction. Or we could set EA minus work of friction is equal to EB minus work of friction is equal to EC. It's really up to you. I would do this top part. So coming back and putting in variables here, EA we said was mg41, and I'm not putting in the mass yet, but I probably should, 33 squared. And that's equal to EB, and at EB we know mg is 0, so mg is 0 plus mvb squared over 2. The reason why I'm not putting in the mass yet is you can see it'll cancel out through everything. So we can find VB here. Since this term goes away, VB, if I multiply through by 2 over m on both sides, I can see that I get 2g times 41 plus 33 squared, and this is b squared, so I need a square root. Now, I told you guys that you can use 10 for g. That makes it a little bit easier because you can just plug in 820 plus 33 times 33, take that square root, and you get 43.69. Is it 44? Oh, it is 44. I'm sorry. So let me fix that. I thought it was 41. Whoops. Did I? I did write 44. Okay. So sorry. Sorry about that, you guys. I hate numbers. So 2 times 44 is 88. 88 times 10 is 880. Square root of 880 plus 33 times 33 is 44.37. So 44.4 meters per second is our velocity when it gets to the bottom of the hill. I'm not going to pull open the, well, I actually do have the test open. So let me see what the other questions were on there. Just really fast. Oh, so this is the, where are you? All right. Yeah, so the first thing is how much work is done by friction when it gets to the thing. We'll get to that in a second. Actually, we'll do that right now because we're at that point. So coming back to this, where we found that, so the work of friction done when you go up a ramp, right, is mu n d. Now, n on a ramp, we already know that n on a ramp is mg cosine because this is n, this is mg cosine, and it can't leave the ramp. So whatever the angle is, we can just get n. But mg cosine of 8 degrees is actually really small. Cosine of 8 degrees is effectively 1 if you put it in your calculator. Cosine of 8 is 0.99. So really, if you want to, and it talks about that in the test, you can just say n is mg. It's close enough that you don't need to put that angle in. So if we do that, we know the work done by friction is the force of friction dotted with d. The force of friction is actually negative mu n, and d is d. But d is also h, on this triangle, right? D here, if we know h, d is equal to h sine theta. I'm sorry, no, it's not. My brain's not working. I knew that as soon as I said it. H2 is that. So H2 is equal to d sine theta, which is equal to h. Why are my mouth and my brain not working together? So d is equal to h over sine theta, right? So this is actually, the work done by friction will be mu n h over sine theta, or plugging in n is mg, negative mg h sine theta. And all I asked for on that was I asked for the symbolic answer there. Does anyone have any questions on why that's negative mu n d? When we do the work, the force of friction is actually backwards, and d is that way as it goes up the ramp. Therefore, because they're off by 180, it picks up a negative sign. This is really force of friction dotted with d is f d cos of the angle between them. They're 180 degrees off. They pick up a negative sign. Okay, so that's that part. What this tells us, though, is we said that EB was equal to EC plus work of friction. And EB we found was MVB squared over 2 because MGHB was 0. EC is going to be 0. And MGH2, that's where it is when it stops. MVC squared over 2. This is going to be 0 because it comes to rest. Work of friction is mu mg h over sine theta. So we can find h2 from this, right? Do you see how we know the angle? we can get rid of the m's, even if we didn't know the m's. We were given mu. So you could find H2 is mg plus mu mg over sine theta, and that's equal to mvb squared, which we just found, over 2. These m's all cancel, and what I get is that H2 is vb squared over 2 times g plus mu g over sine theta. I'm not going to put numbers into that. You guys can if you want. Once you find H2, you can remember that H2 is d sine theta. So you can plug that in or divide through by sine theta and get d and find d. The major thing I want you to take away from this problem is, back when we look at the when we look at this, we just write down the energy here, and the energy here. If there's friction at some point, we need to figure out where to put the friction, and that's a little tricky. You could actually mathematically do it by finding that the energy at C is equal to mgh plus mv squared over 2 minus the work of friction, and that will give you a positive sign because the work of friction is negative. I find it easier just to write E initial is equal to E final plus the work of friction. And then if the friction happens in the middle of a problem, it gets a little worse. It gets a little harder. I probably won't do that to you guys though. And in fact, I'll tell you I won't do that to you. So if the friction's at the end, all you need to remember is that the object stops. If it stops due to friction, it essentially has no energy at that point. This truck does because it has H. So are there any questions on these? There's another problem in the homework where it like goes up and then it hits some friction at the top. This problem right here is essentially this same problem. It starts off with some V and it has a change of height. So the potential energy of gravity changes and you have a loss of friction. And that's all you have to figure out. What this is also saying is that the initial energy went into the final energy at C, which was mgh2, plus the work of friction. So it got divided between the two. This thing has potential energy here, right? So just, if you want to know the algorithm of this, it's at A, B, and C, write down mgh, mv squared over 2. If it had a spring or it was rotating, you would write down the terms for that. And then find your variables, which is what we did here. And then from there, set EA equal to EB equal to EC. If you need to add friction, figure out where you add it. And then it's just solving some algebra that's not that bad. So are there any questions about this problem? Okay, I'm going to assume not. So let's look at this. This problem looks hard. It looks tedious and annoying, and it kind of is. But we can use energy instead of torque to solve this problem. And the only thing you need to remember when you do energy is that, well, I shouldn't say the only thing, but the thing you need to remember is that these pulleys will have I omega squared over 2 if they're rotating. They will pick up rotational. So the energy that each of these things could have is M and M, these are equal, could have mgh and it could have mv squared over 2. This guy falling, again, could also have mgh and mv squared over 2. These pulleys rotating, the only energy they can have is I omega squared over 2. The reason why is that they can't move up or down, so they can't have gravity potential. And they're not going to translate. They're not going to move to the right or left or up or down, so they're not going to have mv squared. But they definitely have I omega squared. Remember too, and this problem is actually really good because at the edge here, both of these pulleys are the same. And so at the edge, you know that A1 and A1, well, A1 here and A1 here have to be the same acceleration. However, this A will be different. this A will be A2, and the reason for that is the whole pulley turns with alpha, but at each point along that pulley, A is different because A is equal to R omega. And V is equal, I'm sorry, A is not equal to R omega. A is equal to R alpha. V is equal to R omega, okay? So we can find them as long as we get our R's correct. We can get these in a form where we can put them all together. And we're gonna see how to do that. I included, I'm gonna post this up, but I included the part that has the numbers on it. I don't really care about the numbers though. So coming back here, what you do in this, if you're gonna do it for energy, is we're gonna assume that it starts from rest. So we're gonna assume that this starts at some height and it ends up at some final height. And this one starts at some initial height and ends up at some final height. And it tells you what it is. And this guy starts at some initial height and ends up at some final height that's negative. And then these pulleys start with omega equal to 0. These guys start with V equal to 0. And V final we will find. V final we will find. And omega final we will find. Sorry, not 0. And this thing will have V initial 0 and then V final. We'll find it, but it'll be negative. And we don't know what it is. So all we really have to do is find the total energy of the whole system. And what I'm going to do is I'm going to write that right here. So the initial energy, we can always assume that these are on their own coordinate systems. They're related, but they're on their own coordinate systems. So we can take H to be 0 here, H to be 0 here, H to be 0 here initially. So our initial energy is M on the left times G times H naught, which is 0, plus M on the right, G H naught, which is 0. I'm going to label this HM so that we're clear that we're not talking about the same. This guy has MGHM naught, and nothing's moving. So they would all have mv squared over 2. There's 2 of those though because we have 2 of these little masses. And really I can just write 2. I could write them separately. I could have wrote 2 MGH there. And then big M, B squared, initial. I guess I should be putting initials on here. And then the pulleys only have I omega squared over 2, and there's 2 of them, omega initial. But all of these things initially are 0. H on the left and H on the right initial are 0. The bars initially at 0. They don't have any initial speed. So the initial energy is 0. On an exam, I'm going to ask you to show that though. Show that the energy is mgh plus mv squared plus I omega squared for the pulleys. And show that you know that you can decide that this is the 0 point for this M, and at the same time, this guy has its own 0. It has its own coordinate system in Y. You don't have to. You could decide that they were a meter apart or something, but don't do that. You don't need to. So once we do that though, we need to look at what is the final energy. And the final energy, M on the left and M on the right, I'm just gonna write 2M. They both rose by H, final. The big M in the middle dropped by H, final big M. So I'm gonna put little legs on it for H final big M, okay? They all have kinetic energy. So the 2, and then the big M gets V final of big M squared over 2. And then finally, the 2 pulleys have I omega final squared over 2. So are you guys okay on that? Finding the energy before and after, that's all you do. Same thing with the truck problem. You just have to figure out what H and what V final are for all of these things. that's going to be a little weird. So we need to find H final for the big mass, and then V final and omega final. Looking at this problem, this V, the V final of the big mass, is equal to R of B. So let me go back here. And actually, I'm going to do this on its own page. I probably should have talked about this first, but for each of these pulleys, you have a pulley A and a pulley B, and they're welded together, okay? And pulley B has this little radius, and pulley A has a bigger radius. But because they're welded together, they have to have the same alpha. They have to have the same omega. They're going to turn at the same rate if they're welded together. I of a pulley is mr squared over 2. So I total will be MA/RA squared over 2 plus MB/RB squared over 2. That is our I for our pulleys. Now we can see that this mass is actually connected at RB, and these little masses on the outside are connected at RA, okay? So what that means is that V at RA is omega A and VA. And V at B is RB omega B. But the omegas are the same for both pulleys. What's going to be different are the radiuses, okay? So when we go back and look at this, when we want to find omega final for the pulleys, we can turn them into either VA over RA, or we could turn it into VB over RB. However, it would be a lot easier if we turn these V's into omegas. Now we know that these two outer masses are at A, so V at A is RA omega final, V final if these are finals. So omega final for this guy, I'm sorry, I don't want to do that. So MV final squared for the two little masses is equal to, if I cancel those, RA squared omega final squared. And for the big guy, it's M over 2, the final M squared is equal to big M over R. Was A in the center? No, A was on the outside. RB omega final squared. And so what I see here is that I've turned these two into omega finals. And what I now have is I have energy initial is equal to energy final, or 0 is equal to little m g h final with 2, there's 2 of those, plus big M g h big M final, plus, if I look at this, little m v, nope, RA squared over 2, there were 2 of them though, so I'll just put a 2 there, times omega final squared, plus big M RB squared over 2 times omega final squared, plus I over 2 omega final squared. Now, as long as I know my HM and my H final for my little ones, I can find this stuff because I've been given M and RB and M and RA. And I know what I is because if you go back to the, where was the beginning of this question? Did I somehow lose? Oh, no. If you go back to this part of it, it tells you that pulley A has a radius of 80 centimeters and 30 centimeters and 3 kilograms and 1 kilogram. So you know those things. It gives you the mass of the bar. It tells you the 2 smaller masses are unknown, but they're equal. Although I think I changed that in this problem. Because you had to find in problem 1 with torque, you had to find what the little masses were. We're going to assume that they're 4.5. So if we assume that they're, I'm sorry, it's now half the value. Yeah, anyway, this is just telling you to call the little masses M1 and M2, but Yeah, I'm sorry. I think in that problem, I haven't, when I did the solutions, I forget what I did. Um, but when you solve this problem, let's just assume you know the M's. We'll talk about it on Monday, how to do it with torque, and it'll make more sense. But it says it goes through one full rotation, okay? And the height, that if you look at these pulleys, if they turn through one rotation, this mass is going to be pulled up by a length or a distance of the circumference. Therefore, assuming that's true, for one rotation, the height change is 2 pi r, wherever that thing's attached, right? So we know H final, if it went through one rotation, would be 2 pi RA. And H final for the big mass, because it's attached at the center B, at the littler pulley, ends up being, ends up being 2 pi RB. So it's turned through an angle of 2 pi rads. The circumference is 2 pi r. And we get that. So if I gave you M and I gave you big M, you could find H final from knowing it went through one rotation. And then you could solve this for omega final. And you can see here that omega final squared would be equal to, if I move this over, -2 little m g h final plus big M g h m final. But note that this will be negative because it's falling. It's falling down. Over all the stuff in front, which is m RA squared plus big M RB squared to the half plus I over 2. And that would be your omega final. Once you had it, you could do something like turn this back into, remember that RA omega final is VA. The mass is on the outside, and that their V initial is 0 and their V final is this VA. And from that, using V final squared minus V initial squared is 2A, Y final minus Y initial. Using the distance, you could find the acceleration. And using V final is equal to V initial plus AT, you could find the time. That stuff you should be able to do. But as far as the setup, what this algorithm is write the energy at each point. So you need to choose 2 points. We chose before it started moving and after it had moved a distance of 1 rotation. Get your variables. And this is where things get a little tricky sometimes, because if it's on an inclined plane, you may have to figure out what H is if you're given some X. You just have to know how to do this. Or if you're told 1 revolution or 2 revolutions or whatever, but 1 revolution would mean 2 pi r change in height for something attached to that pulley. You have to get I sometimes, and usually if the pulleys are welded together, I1 plus I2. And you just have to kind of put the things together, exactly how I put this together. And that's a real pain, to be honest. It's a lot of tedious writing MV squareds and MGHs and keeping everything straight in your head. But if you can do it, it's actually easier than doing torque diagrams, I think. But the point is, in both of these exams, they have to do it by torques in the first problem and do the exact same problem with energy in the second problem. Now, let me ask you something. If the system's moving with constant velocity, can you do it with energy? And the answer is maybe, probably not. Because if it has motion before and motion after, it's going to cancel, right? So you may not, I mean, you could find the change in kinetic energy and set that equal to the change in height, but that would be a horrible problem. So whenever we do energy, the system won't be moving with constant velocity. And the only real thing that you need to remember is that if it's a mass on a pulley, it has these. And if it's a pulley, it has this. Those are the energies that you need to figure out how to write down. There could be friction in there. There probably won't be, because that's just even more complicated. The big mass, the initial height was 0 because we chose it to be 0. What really matters is the potential energy change of these masses, and that's just the change. So we can set our initial height to be 0 for all of them. And then wherever they end up, we just need to make sure that we figure out correctly where they end up. We don't have to have them all in their same coordinate system. You definitely could. I mean, I could tell you that these things are 3 meters below this one, but you really don't need it. You can just assume that they're all at Y initial. You could assume that this problem looks like that they're all aligned to begin with. So this, and I know I just drew that poorly, but so this guy's hooked to the center one, and this one's hooked up there. This one's hooked to the center, and this one's hooked up here. And you can also see that these guys are going to rotate opposite. It doesn't matter when you do energy, because we're doing omega squared in the kinetic energy. It doesn't matter whether they're rotating negative or positive. You don't need to even think about whether they're rotating negative or positive. You do when we do torques. That also makes energy easier. But if we assume they were all level, then they all would have H not equal to 0. The outer ones would have H final equal to something positive, and the inner one would have H final equal to something negative. It would fall, it would rise. And they'll be different because they're at different radiuses. They're going to, if this thing spins around once, the distance this thing drops will be 2 pi RB. It's going to drop a distance of 2 pi RB in one rotation of this pulley. This guy's going to rise 2 pi RA. So this will be negative, this will be positive. I hope that makes sense to you guys. But really, the energy is just figuring out the types of energy it has, and then figuring out your variables, setting the initial equal to the final, and solving for whatever you don't have. You might not have mass, you might not have V, you might not have omega, whatever you don't have. And then the last step is usually converting omega back to V, using V as R omega, or converting V to omega and using constant acceleration or constant angular acceleration. And remember, this is true. And the other version of this for angular rotation is omega final squared minus omega initial squared is 2 alpha angle final minus angle initial. So you could also do this knowing that the change of angle of one rotation is 2 pi. And you found omega final, you could find alpha. And then you could find A at here and A at here using the fact that A is RA alpha for the outer one, and AB is RB alpha for the inner one. So it's not actually hard, but you better do this a few times just to get it straight, where your variables are and how they work together and what you're using to determine things. Now, aside from the test, what I want to tell you is, those of you in biology or some of the other sciences, chemistry, even those of you that are engineers, we're looking at blocks and pulleys here, but these are just models that simplify a system. These could be anything. I mean, to be totally honest with you, anything that has rotating parts and linear translating parts with potential energies. It's a simple model of more complex systems, and you'll do that often. So that's why we're learning it. We're learning how to deal with a system that has potential energy, rotational potential energy, rotational kinetic energy, and kinetic energy. And using those energies to solve for the motion at some final time, assuming we know the motion initially. But for us in practice, all you have to do is go back to this step here where you wrote the initial energy was all the potential energies, all the kinetic energies, and found that these variables were all zero to begin with because it was at rest, and we chose H initial and H initial for big M to be zero. So we got zero. And then for the final, we had all this stuff, and all we had to do was convert these, we had, wherever I wrote it, I don't know, I guess I didn't, I thought I wrote it somewhere, but remember that we had, these were V finals, and we converted them into our omegas. And if you can do that, you're good. The only other weird thing is making sure that you know that it's the total I. This is actually the same picture. If you get this, this is actually the same as if this was somehow connected to, well, I guess I couldn't do that. Never mind. I'll be quiet. I don't want to confuse you more. But yeah, so you just have to know how to find the heights and the velocities and make sure you know I, and you need to understand how this works for different radiuses, how they're related by alpha and omega, but A is different or V is different at each point. Any questions on this that I can answer? Actually, once you do it, it may be daunting if you haven't done it. It might look scary or hard. If you haven't done it before, if you haven't done your homework yet, get on it. But to be honest, it's actually pretty easy because all you have to remember is I omega squared over 2, MV squared over 2, MGH, and then try and find your H's. And remember the rolling without slipping problem, or that A is equal to R alpha, V is equal to R omega. All right, let's leave that behind. I actually—
Can I ask a question real quick? I was just gonna ask, so for the like how you put the two, you like combine the two energies of the mass, that's like give mass, right? Like the same.
Yeah, in this picture, they're the same mass. So I have two of them. I could have written it as M on the left, V squared, you know, over 2, and M on the right, but they're exactly the same. What's kind of messed up with this problem, this problem's a little cruel because it's mean to people that don't know how to do it, but once you know how to do it, because this pulley and this pulley are essentially the same and these masses are the same, it actually looks like a much easier problem where you have a little mass and a big mass. It really does look like this big mass and this little mass, and this is just doubled, and this is doubled. So it's actually a simple problem that was made harder by expanding it and making it look harder, but it's actually a fairly easy Atwood machine. If you don't see that right now, that's totally fine. But it's actually just the Atwood machine example made a little bit harder by reflecting it, which is weird. Yeah, so really what I want to know is that you understand that the accelerations, translational accelerations, are different from alpha, that the pulleys have the same alpha and omega, and that you can find from potential energy and kinetic energy, you can find some velocity and some angular velocity. That's what I'm checking for. But definitely the way you do it is write down the energies, find your variables, set energy initial to energy final, and solve for whatever you're looking for. And you'll get some weird configuration. If you look at the other problem, I don't know where it is, here. So let's look at this really fast. we see that this one's going to rise and this one's going to fall. If we do the energy here, the initial energy, if it starts at rest, this guy has mgh initial plus m1v1 initial squared over 2. This guy has m2 gh2 initial, and I really should put a 1 initial over here, plus m2 v2 initial squared over 2. And each of these pulleys has I omega squared over 2, I omega squared over omega initial squared over 2. Get back to drawing. But this is I1 is just M1 R1 squared over 2. And I2 is, I23 is M2 R2 squared over 2 plus M3 R3 squared over 2. And you can see that that's a combined pulley. So it's going to have the same alpha. Because they're connected at the outer edge, they're going to turn at the same rate. They have to. If the outer edges are turning at the same rate, they have the same alpha 1 is equal to alpha 2, 3, and omega 1 is equal to omega 2, 3. They have to have that if they're connected by stretchless ropes. It's that stupid stretchless rope thing again. But because of that, we also know that A and V, and so V of these are not the same. A at the edge is the same. A inside is not the same. So A2 is going to be equal to R3 alpha, and A1 is going to be equal to R1 alpha. And therefore V1 and V2 will be different because they'll have different accelerations. That's just because they're on different radiuses of the pulleys. But coming back to the full energy here, slide. So what I would write here, I can assume that this guy starts at y initial is 0, and I can assume this guy starts at y initial is 0. Even though they're not at the same height, they have their own coordinates. What I care about is how far it falls. You can see that y final 1 is going to be negative, and y final 2 is going to be positive. I don't know what it is yet. But when I write down the energy initial, all I have to do is write it down for everything. So M1 GH1 initial plus M2 GH2 initial plus M1 V1 initial squared over 2 plus M2 V2 initial squared over 2 plus I1 omega 1 initial squared over 2 plus I2 omega 2 initial squared over 2. But this is really 2, 3, the combined pulley. And if I say this thing starts at rest, which I don't remember if I do or not, system shown is initially at rest, double the values that you found, because this test did the same thing the other one did, where they had to find it by torque and then they had to find it by energy. And when I did that, I think the torque ones were set so that they had constant velocity, meaning the accelerations all canceled. And then I needed to give them a little bit more mass so that it would actually fall and gain some energy. So initially it was like an equilibrium, and now it's not. So ignore that for now. But the initial height, you can assume, is 0. The pulleys don't move, so their initial height doesn't even matter. And what I had them do was write the initial energy just like this. And then all they had to say was H1 initial was equal to H2 initial, was equal to V1 initial, was equal to V2 initial, was equal to omega 1 initial, was equal to omega 2, 3 initial. And these were all 0. These because they were at rest, and these because we chose 0 to be their initial height. I don't know how far it falls. I don't think I grabbed that part of the problem. But let's say it goes through 2 revolutions. If it goes through 2 revolutions, M1 falls 2 pi r times 2. It falls double the circumference. So H1 final would be 2 times 2 pi r1. this guy would rise 2 times 2 pi r3, the center pulley. If the center pulley rotated through 2 complete turns, then mass 2 final would be 2 times 2 pi r3. Does that make sense to you guys? You really have to know how to do that. And some people will not know how to do that. And it's going to confuse them. If the thing goes through 2 complete circles, this mass will rise 2 times 2 pi r. If this one goes through 2 complete circles, this mass will drop 2 pi r1 times 2. That's just the circumference. So knowing that, you can find everything else, because the final energy is, again, M1GH1 final. We just found that. M2GH2 final. And then here's going to be the tricky part. M1V1 final squared plus M2V2 final squared over 2 plus I1 omega final squared over 2 plus I2 omega final, I'm going to call this I23 over 2. But these V's, because they are at different radiuses, these V's are different. So V1 final will equal R1 omega final, and V2 final will equal R2 omega final. They're different because in order for this to turn at a constant alpha, the velocities at each point will be different, and the accelerations at each point will be different. So plugging those in for this, you'll get everything in terms of omega f. Remembering that we basically said E initial was 0, we get that the M1GH1 final, sorry, come on. All right, fine. So minus M1 minus M2GH2 final, that will be equal to all this stuff times omega final squared. And all that stuff is M1 R1 squared over 2 plus M2 R2 squared over 2, and I'm running out of room, sorry, plus I1 over 2 plus I23 over 2. So essentially what's happening here is the change in potential energy of gravity, and remember that H2 final will be positive, H1 final will be negative, so this will be a positive minus a negative. We can tell M1 is bigger than M2, so it's going to drop. So this term will be bigger than this term. And you'll get some positive energy from the change in potential energy. That causes everything to rotate. That's causing the 2 masses to speed up. One's going up, one's going down, but they're speeding up, so they're gaining kinetic energy. And it causes the pulleys to rotate. They're speeding up as they spin around. And that's really physically what's happening here, is the kinetic energy is equal to the change in potential energy. And we know that the initial, so we could say that this is minus M1GH1 initial plus, or sorry, minus M2GH2 initial. But these we already said were 0, and that would be minus all the kinetic energy stuff. And we already said that was equal to 0. So essentially what this all is this is just the change in kinetic energy is equal to the change in potential energy. But we found it by just writing down the final energy and the initial energy and setting them equal. That's really useful. That's really important to know that that's what we're doing. We're just kind of hiding all the math and writing down our equations, which is lazy. If I haven't said it before, physicists are lazy. We don't want to do the hard math. We just want to write down things that we know about the system. And we could do it all with hard math, but we don't need to. We can just write down energies, which is nice. So that's all I want to say about these energy with a pulley and a mass. Unfortunately, your book gives you some examples of this and doesn't do very many homework problems like this. And I think these are the most valuable ones. The truck problem is valuable. You know, it's the normal, just do energy. If you look at the homework, we're going to do one other one in a minute. But if you look at the homework, there's one that like goes out and there's a bobsled that slides down. Those problems are important too. But your book's kind of light on these pulleys with, so rotational motion with linear motion. And that's super important for later on. You need to be able to figure out if a system has linear and angular motion, how they work together. And the fastest way to figure out the motion is just do energy. Just write down the energies and set them equal to each other. And that's what you should be getting out of this. But like I said, the algorithm is just write down the different types of energies that it has, and then figure out what your variables are. Write it for the initial position, write it for the final position, set them equal to each other, and solve. And you may need to flip or may need to substitute in for V to get everything in terms of omega, because you don't have enough equations to solve for V and omega. You would need another equation, and that other equation is actually this one that we're substituting in to get rid of the V's. All right, I want to go to this problem because it's another important problem. This is exactly like the guy skiing in homework 4, I believe. He skis down the hill and he launches into the air, and we want to know how high he hits off that ramp. This is essentially a block, slides to the right, goes up this incline, and launches in the air. When it gets to C, it launches into the air and lands at D. There is friction here. And so this is a problem where we have friction in the middle of the motion. And we're going to need to figure that out. But all you do on these is go back to your algorithm. We have an A, a B, a C, and we do have a D, but I don't want to deal with D. I'm going to deal with D at the end. But A, B, and C, just write down the energies. So the energy at A, the energy at B, and the energy at C. There is no springs, and this is a block. It's not a wheel rotating. It's not a sphere. It's not a cylinder rotating. It's just a block, okay? So I know the only energy this thing can have is mVA squared over 2 plus mgHA, and mVB squared over 2 plus mgHB. If you have a question, just interrupt me. I don't care. I won't think it's rude or get mad. So now our next step is find B and find H for A, B, and C. We also have friction, and we'll get to that. But for now, we know the mass is 5 kilograms. Okay. And from this problem, at position A, it has an unknown initial velocity, slides 15 meters with mu. I'm going to write that down for later. So D is 15 meters, and mu was 0.3. 0.3. The incline is 60 degrees. The hill has a length of 28 meters. We'll talk about that in a minute. It lands 45 meters away and at 5 seconds. So we don't know what this is. We're going to assume that these guys, A and B, are at y is equal to 0. And we don't know what B is. We'll get to what B is in a second, and how we do know what B is. And then C, at the top of the hill, how do we find H if we know the hypotenuse is 28 and the angle is 60? So if the angle is 60 and the hypotenuse is 28, we can find Y, or H, is hypotenuse times sine of 60, right? So what is 28 sine of 60 on your calculator? 28 sine of 60 is 24.25. 24.25. So this is 24.25 meters. That's how high it went up That's the change in potential energy of gravity. So you need to know it. So at C, we don't know what V is, okay? However, the last thing we know, and this sucks because it goes back to our projectile motion, we know that it left with VC at an angle of 60. This was when we did projectile motion and we had V initial, right? We know it's on level ground, and we know that X final was 45 meters and T was 5 meters. I'm sorry, 5 seconds. Okay, and we're going to use G is equal to 10. But from projectile motion, right, we know that X final was equal to V naught of X times T, which was equal to V times cos of 60 times T. And we know that's true. So we can find VC because V is actually VC. And VC here is cos 60 times T over X final. Is everybody with me on that? I know you probably put that out of mind after we got done with example 1, but you still need to know how to do it. So we know that VC is, what was it, cos 60 times T over X final, and you were given T and X final. So we can find VC. And now here's the part that this problem gets tricky. The energy at A is equal to the energy at B plus the work of friction. But this, it's actually easier to write it this way. The energy at A minus the work of friction is equal to the energy at B. So as it went from A to B, there was friction there. The reason why we want to do that is after the friction's gone, E at B is equal to E at C. And it's also equal to E at D, to tell you the truth, but we're not interested in D. So we know that this is E of C. If we go back here and we look at this stuff, we know that we don't know. We know that MVA is something. MGHA is 0. And I wish my computer would stop doing that. It's generating an auto recovery file for some stupid reason every time I do. Minus the work of friction. Now the work of friction, this thing's on level ground. The work is mu n, but n is mg because it's on level ground. So this is mu mg times d. That's the work of friction. This is equal to the energy at B, and it's equal to the energy at C. Now, we know this is 0. Okay, we know what this is. We were given all of this in our problem statement. We found HC. HC was, H was our 28 sine of 60. We found VC from cos 60 times T over X final. And from that, oh God, I'm so being dumb. I can't do math. Sorry, you guys, you should stop me. That was done really badly. VC is X final over T cos theta. So I had that flipped. Algebra's a killer. I'm sorry. Always, always a killer. X final over cos theta T. And here, and X final over cos theta T. I'm sorry about that, you guys. So we know VC and we know HC. We know this, and so we could either find VB or we could find VA. And we would have that MVA squared minus mu MGD is equal to either MVB squared over 2 or is equal to M times X final over cos theta times T squared over 2 plus MG, I guess L sine theta, right? And that's all you have to do. You can answer everything else in this problem, but this problem is hard because you're working backwards. It's kind of like the ballistic pendulum, in that you're working backwards through the different types of energy to get VA, because VA was the thing that we didn't know. We find this from this, then we use these to find B, and then we use these to find A. Although you could skip this because you don't need it. You could just set energy at A equal to energy at C, to be honest. I don't know if I asked anything else on there. I'm sure that whatever else I asked wasn't hard. It was either using projectile motion or just asking what is VB and then asking what is VA or what is the work of friction. Generally in the problems, I try to break them up into steps so that you can follow the steps, and like it kind of tells you what to do next if you were lost and didn't know. So if I'm asking for something and you don't know why I'm asking for it, maybe look at the previous step, and that will tell you like what you need to do if you didn't, if you know what I mean. It's supposed to flow in a logical manner. And unfortunately, it flows in a logical manner for me, which is not always logical for you guys, or for all of you anyway. Okay, any questions on that? This problem is the essence of energy. And if you go back and look at that homework problem with the guy on the ski jump, it's the same exact problem as the ski jump. It's just in that problem, he starts from a height, then he launches. And it's problem 822 in homework 5, I believe. Homework 4, I mean. All right. So now
I have a quick question about when you're calculating these. So whenever we're doing trig for like problems like this, we need to be in degree mode, right? But whenever there's like rotation or we're doing the torques, we need to be in radian, right?
What you need to remember is that you need to be, sometimes you need it to give you a number. So trying to think. We'll get back to that. Here it doesn't matter. You could put it in 60 degrees or you could put it in there. What matters is when you're talking about rotations through angles. So it really matters with torque more than this stuff. And the reason why it matters for torque is that torque is actually times the change in angle gives you energy, gives you rotation. And a lot of times you don't realize that you're finding like arc sine of something to get the angle. But if you put the change of angle in here as degrees, degrees don't mean anything. They're basically just a division of a circle into 360 parts. So it has to be in radians, because radians are actually a real length. They don't have units, but they're an actual length. So on Monday, we'll talk about that. Just, you need to make sure that if you're taking the arc of an angle and you need an angle for something, I would put it in radians. Don't put it in degrees. Although it's hard, because honestly, you don't have to put this one into degrees, or I mean into radians. You can use sine of 60. It comes up because the one thing that I like to use is, you don't realize it, but your circumference is actually your change of angle times r, and your change of angle is the complete loop. If you use 360 degrees, your circumference is not 360 times r. It's 2 pi rad times r, right? So there's times where you can't use angle in degrees, and you just need to make sure that you know when you need it to be in radians and when you can just put it in there. I'm trying to think in my head right now, and I can't remember it. There's a few classic examples of where you want it in degrees and where you want it in radians. But
okay.
I think this one works. I mean, showing you the circumference, you understand that the circumference can't be 360R. I think we
Yeah.
all understand that.
So what about for the problem we were doing earlier when we were trying to calculate the length, and then it said you were saying that it went around the pulley went through 2 revolutions, so it'd be 4 pi r.
Right.
Would that matter if we were in?
Yeah, because that would be 720 degrees times r wouldn't give you a good number.
Right. Yeah. So you'd have to be in radians for that one for sure.
Yeah, and what it really is that the arc length is SR change of theta, really. I mean, this circumference, I'm really saying circumference is the arc length, where the change of angle is 2 pi, or it's 4 pi, or it's 8 pi, or whatever. Also, that if you know that I should have brought this up, but let's say you know that this thing has a pulley with a radius of 0.2 or something, and this thing's on the edge, and you know it falls a height of 15 meters, right? If I want to know how many times did this go around as the block fell 15 meters, you would have to say S is R delta theta. And so S over R, where S is going to be your 15 meters over your R, gives you your change of angle. Divide that by 2 pi to get how many times it went around. That might show up, but I won't do that to you because we haven't really done that at all. But you could definitely, so 15 divided by 0.2, 0.2 is 1/5, that's 75, right? And 75 divided by 2 pi per revolution, this is 75 rads, would give you whatever, 75 divided by 2 pi is about 12 revolutions, that's 11.9. So when something with a radius of 0.2 goes around almost 12 times, it passes through 75 rad. It goes through 2 pi rad every time it goes around. So that's essentially a little more than 6. 2 pi is a little more than 6 times 12 is 75. So yeah, just make sure you know that you can figure that out if you needed to. That's pretty basic geometry. I probably won't ask that though, just because there's so many people that haven't had to do it before. And I at least want you to see everything that's on the test, have seen it in a homework, in a quiz, or in review, on a practice exam. Okay. So the energy is only going to be 1 or 2 questions, right? The other thing that we learned in chapters 7, 8, and 9 is all momentum. And there were a couple problems in the homework, but I just want to go over this again and make sure you remember it. Elastic collisions, and there's always mass 2 at rest. So mass 1 has some V, and mass 2 V initial, and mass 2 is at rest. And then afterwards, we don't know. In general, mass 2 is always going to be going in the same direction that mass 1 was originally going, if it's at rest. But we don't know what V final for 1 is. We can use the equations, and this is V1 initial. We have these equations that all you have to do is plug numbers in. If you want to find V final for mass 1, it's M1 minus M2 over M1 plus M2. They're in your book, in the chapter. They're a little annoying to find sometimes. I sometimes have trouble figuring out what page they're on. But this tells you, you can see here that V2 final is always going to be positive. But V1 final is either positive or negative or 0, depending on what M1 and M2 are. If M1 is greater than M2, then V1 final is positive. If M1 is less than M2, then V1 final is negative. And what that means is, if this is a marble, M2 is a bowling ball, it hits and it bounces off and goes back the other way. If M1 is a bowling ball and M2 is a marble, it hits it and rolls over it, right? And if they're the same, what happens is, if M1 equals M2, then we get V1 final is 0. If they're equal, they hit, all the momentum moves from here to here. Now, how we're actually doing that, though, is we're saying the initial momentum, P, which is mv, so m1 v1 initial plus m2 v2 initial is equal to P final, which is m1 v1 final plus m2 v2 final. And only for elastic, the kinetic energy is conserved, which means m1 v1 initial squared over 2 plus m2 v2 initial squared over 2 is equal to m1 v1 final squared over 2 plus m2 v2 final squared over 2. And this would be 0 and this would be 0. So you can figure out if you know one of these and you know initial, or you could, if I gave you initial, you could just plug them into here and get this. These are actually from, this is the changing kinetic energy is 0. You're plugging these into this to get these two equations anyway. So just know that. In contrast, inelastic means that they stick. And if they stick together, if M1 is again moving with V1 initial and M2 is at rest, afterwards they stick together and they head off with V final. Here, P initial is M1 V1 initial plus, did I not square? Good. Plus M2 V2 initial is equal to M1 plus M2 V2 or V final. Now here, the kinetic energy is not 0. In fact, it's always negative. And the reason why that is you can see that V final is going to be M1 over M1 plus M2 times V1 initial. And so the change in kinetic energy will be M1, M1 plus M2, change is always final, minus M1 V1 initial squared over 2. And this will always be less than this because of this, you're dividing by M1 plus M2. So you know that the change in kinetic energy is always negative when things stick together. You could find the change in kinetic energy here. Here you could use the fact that they're equal to find the final, or you could tell me what the final is and verify it by finding this and setting them equal and making sure that they're the same. Here, you always, in an inelastic, you always are talking about what is the change, and it's always negative. The reason why it's negative is they heat up or intermolecular forces have to be broken or whatever for them to stick together. It always loses some energy when they stick. So there's like 4 examples of this, 2 interactive and 2 afterwards. You'll always be told that something's elastic if they bounce. If they hit each other and they bounce off, it's elastic. If they hit and they stick, it's inelastic. If you don't know, assume it's inelastic. So don't know, you start by saying M1 V1 initial squared over, no, don't do that, James. Start with momentum. And you know that the momentum's always conserved, okay? Always conserved. This is always true, and we could have a million particles, it doesn't matter, or we should just have 1 particle. Then check and see if M1 V1 initial squared plus M2 V2 initial squared over 2 is equal to M1 V1 final squared over 2 plus M2 V2 final squared over 2. If you don't know, assume that this is not equal, okay? Assume that there's just a change. What this leads to, though, is with inelastic collisions, we already know this, we just did this. And if the change of momentum, the change of MV is equal to the force times time. So if the change in momentum is not conserved, I guess I shouldn't say that. Inelastic collisions don't lead to that because it is conserved. If the change of momentum is not 0, then you have an impulse. And the impulse is what we did in the lab last week. F times T is MV final minus MV initial. And you guys should know that. That's super easy. Plug in numbers, to be honest with you. But like the baseball problem I did in lecture, it's almost too simple to even ask good questions about, because there's just not enough here to ask about. It might show up at the end of a question, but it's not going to be by itself. What you might have happen to make momentum complicated is if you look at this, and this is just two-dimensional inelastic. The only difference between what I showed you before and this is that you have to do X and Y separately. So MV1 initial in the X for M1 plus M2 V2 initial in the X is equal to M1 V1 final in the X plus M2 V2 final in the X. Sorry, I don't know why I wrote an F there. And the kinetic energies as well. And it's the same thing that you do in one dimension. You just do it in X and do it in Y separately, and then combine that V final is V final in the Y, or in the X squared plus V final in the Y squared. You just sum them together. This isn't that hard, to be honest with you. I don't even want to go over this. It would take a bunch of time, and it's super easy to do. I believe there is this example in the book, and you can just look at it, but it's super easy. It's just doing the inelastic collision in X and doing it in Y, and then putting them together to find the angle. And the angle here would be arctan of Vy over Vx, if you wanted it from here. That's pretty easy. The last thing that I wanted, I guess that might be, what about this one? No, that was already done. So yeah, to be honest with you, what you need to know how to do is make sure you know how to do energy for like the truck, or just like free fall, or something where the guy flying off the ramp. Know how to do that energy. Know how to do energy when you have masses and pulleys. Okay, and then for momentum, know the difference between elastic and inelastic, and know how to find here KE conserved. So delta KE is 0. Here KE not conserved. So delta KE is always some negative due to heat. And the last thing really that we needed to cover in here was impulse. And we covered that in the lab, and there was one or two impulse, which is FT is equal to MV final minus MV initial. The only hard thing here was that you could mess up is if you forgot that something coming into a collision, V initial would be negative, and as it leaves, V final would be positive. So this is positive minus a minus. You get the total change in momentum is the impulse. But I think you guys probably really understand that. And the momentum problems are really just plugging numbers into the right equation. So make sure you know which equation applies to which case. Inelastic means they stick together and they waste energy by bonding. Elastic means they bounce off each other and they don't lose any energy at all. And if you don't know, assume it's inelastic and find out if the kinetic energy is conserved or not. But in general, you'll totally know, unless I'm trying to be tricky. The last thing I want to cover, though, is I want to cover a couple of fun, weird momentum problems. And I want to show you guys something. There's a Superman problem that you might not have done yet, but I hope you did on the homework. where you have a bullet coming in with some V initial, and it bounces off Superman's chest. And it says that V initial and V final have the same magnitude of like 300 meters per second. And they give you that there's like 120 bullets per minute, okay? And they want to know the power, right? So they want to know the power of that, which is the work over time. And I take you guys through that, and that's all well and cool. But basically, work, remember, is force and distance. I forget how they, let me see something really fast. I'm going to switch over to our module. In my solutions, that was homework 5, right? So when we talk about Superman, oh, and I'll talk about this problem, but so we want the force is power over time. I'm sorry, the force is the change of momentum over time. I don't know why I was thinking that it was power. I'm being dumb. My brain's not working. So let me go back to this. So this is delta P, this is not power. In fact, erase all this stupid stuff. So for this problem, force times T is equal to change of momentum. And what we want to know is the change of momentum over T to get the force, right? So to find this force, divide through by T. And we want to know the force of these bullets on him. The change in momentum is just the change in MB, so it's MB final minus MB initial. And if the mass of the bullet is given as like 0.006 kilograms, we could plug in the mass and we could plug in the velocities and find that. Divide it by the time, and so what we actually would multiply this by is 120 divided by 60 seconds in a minute, right? To get 2 bullets per second hit him. And so if we multiply the 120, the momentum of 120, sorry, I'm trying to do this in my head. The momentum would actually be 2 bullets per second times the momentum of each bullet, which is times MB final minus MB initial. And that would be the total momentum per second is equal to the force on him per second. And you get some number and you find out what that force is. If this were 0.006 and these were 300, that would be 600 times 0.006. 600 times 0.006 is 3.6 times 2. It's only a force of 7.2 newtons per second, which is nothing. This was huge because, I don't know why it was huge. It was 360. Oh, oh no, it wasn't huge, I'm sorry. In that answer, it was like 10 newtons, which is nothing. So the force of the bullets hitting him and bouncing off, if they were bouncing off, is only 10 newtons, which is nothing. Okay, so what I want to talk about is similar to this. I gave them a cool problem, and I'm going to turn my camera on for a second. So this thing right here, if you can see it, I don't know if you can see it, but this thing is really hard to see. It's called a radiometer. And how it works is you would think that if you shine a light on it, I'm trying not to make it bounce around too much, but if I shine my light on it, it starts spinning. I don't know if you saw that, but it totally starts spinning. And you would think that these little fins, because they're white and black, that this is like each fin, you have a photon coming in, hitting it and bouncing off. And when it bounces off, it makes this thing rotate. And so what I have you do in this test problem is you have the energy of the mass coming in and leaving. I'm sorry, the change in potential, or the change in momentum of the photons. That change in momentum has to be equal to the change in momentum of I omega. We haven't talked about this, but just so you guys know, this, if we turn omega into V over R, and we notice that I is mr squared times V over R, what we get is mvr. That's what we're going to do after the exam. But for now, just know that this is angular momentum. It's the angular analog to mv is I omega. So whatever change here happens, you get the same change here. And what you would think is happening when you look at that problem is it's hitting and bouncing off and causing this thing to rotate around. And we'll talk about this on Monday about like using I when I isn't something you just write down. For energy, you'll just write down what the I's are. But here, the moment of inertia depends on how far away it is from the axis. And you think this is light. Turns out it's not light. It's not the light photons hitting that white square and driving it around. It's heat emission if you cover this thing with your hand. If I hold my hand over it, it eventually heats up enough, maybe not, that it'll start turning once the air gets hot enough in there. Because the cool side, the black side spins, it's not doing it right now, which is fine. But you can watch videos on these things. And if you get it heated up by your hand and rotating, I guess I could somehow, maybe it's just too cold in here right now. But eventually what will happen is the air will heat up inside there. And the emission of heat off the black squares and off the white squares is different, which will make the heating and cooling determine whether or not this thing rotates. If I can get it to spin after I heat it up, what's weird is if I shove it in my freezer and cool it off, it'll be spinning the other way after a few minutes. They're called radiometers, and they're pretty cool, but they demonstrate change of momentum causing force. Basically, the change of momentum on here causes an equal and opposite force on whatever that is. If you go through that problem, just know that you don't need to understand that problem right now because that problem relies on conservation of angular momentum. But I wanted to talk to you guys about it because it's actually kind of cool. It's a cool problem. And you can find these, I guess, at like little educational stores. You can buy them if you didn't know what they are or you didn't know how they worked. They don't work by light bouncing off them. They work by the heat of the air inside it being hotter than the surface of the little fins, which is cool, or cooler than the other side. Anyway, do you guys have any questions on specific homework problems or exam problems that maybe you've looked at already and didn't understand yet? If it's torque, we're going to do it on Monday. So really, I just want to talk about energy and collisions. If not, we can be done and I can put this online for you guys. Otherwise, I'm good. So.
Can we do number 19 on chapter 7 homework?
What is number 19?
It's when he's like trying to pull something up, but then the string is gone.
Number 19 on which homework? I'm sorry, Calvin, which homework?
Homework number 4.
Homework 4. number 19 eventually. Oh, this. Yeah. So the idea here is that, let me go back to this. The idea here is to understand work and potential energy of gravity. So let's talk about it without the force there, is really the first thing that we should talk about. So if there's no force, and this is at some angle, right? And we know the height, it doesn't matter, but we know the height and there's no friction here. At A and at B, when it gets to the bottom, what is the energy? Assuming that it starts with some velocity. What is the velocity at the bottom? Well, mva squared over 2 plus mgha, and then at the bottom, mvb squared over 2 plus mghb. And we're going to assume that HA is greater than HB, okay? So what we get if we set these things equal to each other, plus MGHA is equal to MVB squared over 2 plus MGHB. And just for, I'm going to say that HB is 0, just to make this faster for me. So I have that MVA squared over 2 minus MVB squared over 2 is equal to negative MGHA, right? The reason why is VA is actually going to be less than VB. This side will be negative. So the change in kinetic energy and the change in potential energy, this would really be MGHB, but it's 0, right? So this is minus the change in potential energy of gravity. Now, if I have a guy holding a force on it and it slides a distance d down, where d is equal to, h is equal to d sine theta, so d is equal to h over sine theta. But when it goes down, the work done by that force, because it's pulling up, is F dot D. D is down, so F is positive, D is negative, and I get negative F times H over sine theta. So now, if I look at this, the change in kinetic energy has to be equal to the change in potential energy plus the work of this force. The change in potential energy is mghb minus mgha, but with a negative sign. Yeah. Oh, I'm sorry. That's a negative. So I know what's going. I'm being stupid. So again, I know a lot of you had questions on this. The potential energy of gravity change is mgh final minus mgh initial. So this would be mghb minus mgha, which means that I've got this backwards here. And why is it backwards? What did I do wrong? So why is my thing being weird? Oh, because I'm dumb. So the change in potential energy, don't do that. The negative change in potential energy is mgha minus mghb, or mgh initial minus mgh final. And here, this is bothering me because what I should get is that the change in kinetic energy is the negative of the change in potential, which should give me that mvb squared over 2 minus mva squared over 2 is equal to mgha, yeah, that's right, mghb What did I say here? I haven't flipped. I'm sorry. I'm not used to really doing it this way because I rarely ever do it this way. But this would be HA minus MGHB, which means that the change in potential energy will be positive. This will be negative, which is because yeah, my brain just decided to check out. This is true, and this is the negative potential. This is kinetic. So what do I have mixed up here? Oh, I'm so sorry, you guys. Yell at me, please, when I do something stupid. VB, VA. Okay. VA will be less than VB because it slides down, it picks up speed. That's equal to MGHA minus MGHB, which is the initial minus the final, which is actually backwards from what we normally say the delta is. The delta should be MGH final minus MGH initial. It's flipped here. And the reason why it's flipped is because this work is negative. Sorry. The work of gravity is negative. And when you do the work of gravity, you end up getting MGH initial minus MGH final because that negative sign. How you remember that is that MVA squared over 2 plus MGHA has to equal MVB squared over 2 plus MGHB. If I put the MGHs on the same side, I get MGHB minus well, let me put them on the other side actually. MGHA minus MGHB is equal to MVB squared over 2 minus MVA squared over 2. We can think of this as the kinetic energy final minus the kinetic energy initial, and this is the potential energy initial of gravity minus the potential energy final. This is negative delta PE, this is positive delta KE, and the reason for it is we can choose our 0 point anywhere we want, so the change in kinetic energy plus the change in potential energy has to equal 0. Whatever one of them changes, the other one changes. Therefore, delta kinetic energy is negative potential energy. When we do that, so back to this problem with the guy with the rope and the block, we have that the kinetic energy change is the negative of the potential energy change, but we also have some force. So delta KE plus delta PE plus the work done by this force have to equal 0. And that means that the kinetic energy is equal to negative delta PE minus the work of this force. And the work of this force is F dot D. The force is pulling up, D is going down. That means that this is negative FD is this force. And we get that this is negative PE or MGH initial minus MGH final, or B minus A, minus a minus plus FD, okay? So the change in kinetic energy minus, I know what the question asks. The question asks, so what would the change be without that force? And the change would just be MGH initial minus MGH final without that force. What you would gain is delta KE would be minus the work of that force. Sorry, plus. It's weird. It's a weirdly worded problem. Essentially what they're saying is without that force on there, how much faster would this thing be going, or how much greater would the change of potential energy be? Well, it would be greater by the work of that force. And the work of that force is FD. Whatever that force happened to be times the distance it went down. I hope that makes sense. I know I'm like tongue-tied today, and I'm sorry about that. But the change in kinetic energy is equal to the negative of the change in potential energy minus the work done by that force. So without that force, how much greater would the kinetic energy be? Well, you just add the energy due to that force, because that force is trying to stop it from sliding down the hill, right? It's a weird problem. Did that answer it for you, Calvin?
Yeah.
Okay. I know it's weird trying to deal with these negative signs are always a pain. And I may have it wrong. That negative sign feels wrong to me. My intuition says it was wrong, but you guys are going to find that intuition often hurts you more than it helps you in physics. When you think you're sure that something's negative or positive, it turns out you're totally wrong. So I think that's right. But basically, the potential energy is being, the kinetic energy that would be gained from the change in potential energy is being reduced by the work of that force. So this would be positive mg initial minus mg final. And so this actually would be negative, but this guy would be negative too. So really what you get is you get, yeah, that sign's wrong. That sign should be positive. This should be negative here. What you get on this side is mva vb squared over 2 mva squared over 2 is equal to mgha minus mghb minus, so plus work of this force. This, if it started at rest and it ended at 0, would say that mbb over 2 is equal to mgha, and then minus the work of that force. And because that force and the displacement are in opposite directions, it has a minus sign on it. That's right. That's correct. So it would be minus. My intuition was right. Anyway, don't forget also that during the exam, if there's a question about a minus sign you have, just ask me. I'm more than happy to tell you if your sign's wrong. This stuff is hard. I don't know what to say. But anyway, so on Sunday, I'm going to post the solutions to the exams. I already have them. Calvin already has them, if you want them from Calvin. Calvin asked them for me, from me. I don't want to put them online because there's some people that don't want them. They want to try and do it without access to them. So I'll post them Sunday morning like normal. And I'll post the solutions to homework 6 and 7 Sunday morning. And Monday we'll go over the torque stuff, the how to deal with torques and how to deal with rotation from torques. The rest of the problems on these exams. But otherwise, I'm all good. If anyone has any more questions, let me know. Otherwise, we can be done. All righty. Bye, everybody. I'll post this video soon.